Welcome to this video on analog to digital and digital to analog conversion. I'll show you some theory and we'll create a circuit on Multisim. The ADC is made up of an analog input, comparators and some logic. An analog signal such as music, a voice or a signal from a transducer is fed into the comparators, which compare the input to preset threshold voltages. The comparator outputs are fed into a logic section which create binary values corresponding to the input voltage. We could store the binary data or transmit it, and in this video we use a DAC which is made up of a summing amplifier and a low pass filter, a digital to analog converter. The ADC logic feeds the summing amplifier, and the summing amplifier provides discrete voltages which approximate the analog input signal. The amplifier output is not of much use to us, so it's filtered to remove high frequencies from the digitizing process. And the filter's analog output ideally matches the original analog input as best as it can. So we end up with a copy of our original analog input. Here's the original input voltage and here's the final analog voltage in purple. And they're never going to be exactly the same, but we want them to be as good as possible. The ADC takes a continuous analog signal and digitizes it into discrete voltage approximations, and the DAC reverses this process. The more digital voltage levels we have, the better the approximation is. So there's our ADC and DAC on Multisim, which I'll share with you later. We have an input voltage from a mic, and I've used just a 1 Hz sine wave with a 4 volts peak. There's 8 comparators in this circuit, and they compare the input voltage, the analog voltage, against preset threshold voltages. Then we have some logic to take those comparator outputs and create binary coded decimal outputs. Then the DAC starts with a summing amplifier with binary weighted inputs, and this is based on an inverting op-amp. So we need another inverting op-amp, a simple one, just to turn the digital approximation back the right way round. Finally, we have a low pass filter on the output and an inverting amplifier, and this boosts and filters the digitized voltage into a nice smooth analog voltage. The analog input is fed to several comparators, each of which has a different threshold voltage which is compared to Vin. Here the thresholds are 0.5, 0 and minus 0.5 volts. The top op-amp will output high when Vin is greater than the 0.5 threshold presented to its inverting input. The second op-amp will go high when Vin is above 0 volts, which is its threshold. The third op-amp will output high when Vin goes below 0 volts, as 0 volts is the non-inverting input threshold to that op-amp. And the bottom op-amp will output high when Vin drives its inverting input below the minus 0.5 volts threshold. More comparators means better resolution and more accurate input approximations are made. So on Multisim we'll get an op-amp, just a simple 3-terminal one. And I've got 8 comparators, so we'll have 8 of these, but importantly we want the positive output swing to be 5 volts and the negative swing to be 0 volts rather than plus or minus 15 like we usually use. So grab this one, call it op-amp 8, and then duplicate so that there are 8 of them. And this ground will be the threshold voltage for the 2 middle op-amps. We need some resistors to make the voltage thresholds. They will divide a DC voltage to give different thresholds. I'm using a 4 volt sinusoidal input, so I need a voltage below that, say about 3 volts for the thresholds. There's a DC voltage which will create our different voltage thresholds to compare to Vin. I'm going to make that 3 volts, and then we'll have 3, 2, 1 and 0 volt thresholds for those 4 op amps. They're for the positive part of the sine wave. As Vin increases past these thresholds, more op amps will output a logic high. This circuit though cannot detect any input changes of less than 1 volt, so it's good as a demonstrator, but you wouldn't want this circuit in real life. We're going to get a manual test input voltage with a plus or minus 4 volts swing. It's a DC voltage. We'll change the percentage on the potentiometer to change the input voltage, which is like our signal, our audio signal if you like. Feed this into all of the op amps, the top 4 at least for now. We'll grab 4 LEDs and current limiting resistors, just 220 ohms, so the LEDs wouldn't burn out in real life. Put a voltage probe on the voltage input. I'll call it Vin or input voltage, something like that. And then do an interactive real-time simulation. At the moment, the input voltage is below 0 volts, so no LEDs are lit. But as Vin goes greater than 0 volts, LED 5 lights up. And then as we change the potentiometer percentage, you can see the input voltage approaching 1 volt, and now LED 6 lights up when Vin is greater than 1. When Vin is greater than 2 volts, we'll see LED 7 light up, and when Vin is greater than positive 3 volts, we will see LED 8 light up. There it goes. So that works well for now. Next we'll do the same for the negative half cycle of the sine wave. We'll add some more LEDs for the other 4 op amps. It's pretty much a mirror image, but there are some differences as to where the threshold voltages are on the op amps. When the non-inverting voltage is greater than the inverting voltage for these op amps, the op amps will swing high, even if both inputs to them are negative. So this is a 3 volt supply, but it gives us 0, -1, -2 and -3 volts. And as Vin decreases below these negative threshold voltages, more non-inverting inputs become relatively more positive, so more op amps will output a logic high, that is 5 volts. And all op amps are wired to the same input voltage, of course, our audio or music voltage. Now we'll test the other LEDs and op amps. So Vin is 0, so nothing is lit. And as Vin goes below 0, LED 4 lights. When Vin is less than -1 volts, which is the threshold, the next LED lights, and so on. Finally, when Vin is less than -3 volts, LED 1 lights. So that's working well. I'll save it with sine on the end, so I've got a backup of my circuit. I'm going to get rid of the manual input, and I'm going to get a sine wave AC voltage input. Put the voltage probe on the input signal, and it's going to be a 4 volt peak, and I'm just going to simulate at 1 hertz. And then we'll do our interactive simulation, press play, but then you'll notice the LEDs are flashing so fast because Multisim's simulating it too fast rather than real time. So I'll press stop and I'll make Multisim work harder. Instead of a calculation every 10 microseconds, I'll make it do a calculation every single microsecond. And this animation shows exactly what's going on. Analog input passing various thresholds, and then the different LEDs light, which means that the op-amp outputs are going high at that point. So we're going to get rid of the LEDs and we're just going to place some voltage probes on the op-amp outputs so that we can do a graph trace when we simulate. So we need voltage probes, best to label them properly so you know what they represent, and we need 8 of those. Do a transient analysis in time. I'm going to end it at 3 seconds. You could do 2 seconds at 1 Hertz. And we've got our maximum time step of 3 microseconds, which is a good in-between amount to use. There's our input voltage, and this shows as V in is greater than 3 volts, op-amp 8 goes high, V in is greater than 2, op-amp 7 goes high, and so on. Finally, when V in is less than -3 volts, op-amp 1 goes high. So for our summing amplifier, we need an op-amp, but we're going to give it a normal voltage swing of about plus or minus 20 volts because it's an inverting amplifier and a summing amplifier. And we'll change the symbol so it looks more familiar for an inverting op-amp summing amplifier. Then we need 3 input resistors and a feedback resistor, and the gain of each input branch is minus RF over Rin. And because this is a binary weighted summing amplifier, each branch will have a binary gain. So I'm going to make the feedback resistor 16K, then R9 will become RA. So the required gains we need are 1, 2 and 4 for the binary number system. So RA needs to be 16K, RB 8K, and RC needs to be a 4K resistor. And that's that for our summing amplifier. This table shows how the op-amps go high on their outputs as the input voltage changes, but importantly we want to look at the digital to analog converter inputs in blue on the right, the last 3 columns, because we need to come up with binary coded decimal numbers and Boolean expressions, for instance C equals, B equals and A equals, in terms of the op-amp outputs 1 to 8. So for summing amplifier C input, you'll notice that it's always on only when 5 is high. So in Boolean expressions, C equals op-amp 5 or C equals 5. Then B equals 7 and 6 or 4 and not 2. And this can be simplified if you notice how. Then finally, input A to the DAC, A equals 8 or not 7 and 6 or 4 and not 3 or 2 and not 1. And that's it for the logic section. I'll put a reminder of those Boolean expressions at the top, and we need some logic that represents those Boolean expressions. 1, 2, 3, 4, 5 2-input AND gates. We need inverters or NOT gates. And we need 1, 2, 3, 4 of those. We need a 2-input OR gate for B. And we need a 4-input OR gate for A. And we'll just move them out of the way for now and wire it up. The C equals 5, so we wire RC to op amp 5, and that's done. Then B equals 7 and 6, or 4 and not 2. So here we'll do 6 and 7, which is the same thing, and wire up to 4, get a NOT gate from 2, and then we have 4 and not 2, and that's B done. Then for binary A in the summing amplifier, A is equal to 6 and not 7, or 4 ANDed with not 3, or 2 ANDed with not 1. Put those 3 into the 4 input OR gate, but don't forget that A also includes 8 as an odd term. So we'll wire that up to 8. And we're fully done now for the summing amplifier digital to analog conversion input part. Put a probe on the output V out, and then simulate and have a look what it looks like. And it works okay, but we can see that the output is clipping as the analog input goes high. That just means that the gain is too high for our summing amplifier. So instead of having a 16K feedback resistor, I'm going to make it a 3K, and that's the only resistor that you need to change. Let's do an automatic time step and resimulate because it's quicker. It looks a lot better now, but we do have some glitches where the analog input crosses the 0 volts threshold. But we can fix this. It's to do with op amps 5 and 4, and as op amp 4 goes low and op amp 5 goes high, or vice versa, this is the time when the glitch happens. But because the glitch only lasts for 12 microseconds, it'll be filtered out later by the low pass filter. But we can make it better in the meantime. Notice that op amp 5 is the only op amp that goes directly to the summing amplifier. It has no logic associated with it, and logic always introduces a slight delay, so it'll arrive faster. So what we're going to do is put 2 NOT gates in to give a little bit of delay to the signal, but it won't change its Boolean state. So now it's a lot better. Most of the glitches are gone. There's only tiny ones which we can deal with later. We'll just invert this digital output so it's the right way round, because we used an inverting op amp for the summing amplifier. Dead simple. Feedback resistor, input resistor, feed it through that. A gain of 1 so we don't change the overall height of the output. And this is exactly what we're looking for, a digitized sine wave. Now we're going to low pass filter the digitized output so that all the high frequency harmonics are removed. We'll just move this over. We need a resistor and capacitor for our low pass filter. Remember, we've got just a 1 Hz pure sine wave as our analog input voltage. Feed the output through the filter, then it can go through the inverting amplifier. So the cutoff frequency for this circuit, it equals 1 Hz because that's the highest frequency of our input, but it also equals 1 over 2 pi R4C1. So we can rearrange to find out what capacitor we need if we've got a 1K resistor. And that's 1 over 2 pi times R4 times F, the frequency, which is 1 Hz. So that gives us 159.2 microfarads. So we'll just change C1 to that value. I'll change the output trace to blue and make it a little thicker so it stands out. We'll have a look at that shortly. I need another inverting amplifier to show us the digitized voltage the right way around. I've called that V out not smooth, which is a terrible name to give it, to be honest. Resimulate. And there we are. See, analog input, digital out, and analog output. So the analog output is a good representation of our input for this simple circuit. We're going to make a sample and hold sub-circuit. Sample and hold latches or freezes the ADC outputs extremely frequently. This synchronizes the asynchronous logic outputs so that they have well-defined logic levels. So the values cannot change between samples, which is good for processing. So get rid of those two time delay NOT gates. We don't need those. We've got 3 D-type flip-flops wired up to C, B and A. And we will clock these synchronously. And what it'll do is basically look at what the logic levels are from the logic section several times a second. So everything will be well defined. It's not good to have asynchronous signals in such a circuit. Clock them all together. I'm going to clock these at 50 Hertz. In real life circuits, you need to clock them twice as fast as your highest input frequency, called the Nyquist rate. Click on Simulate. We've got the input, the digital output and the analog output. So it's looking pretty good. There are no glitches at all now on the digitized output. Now for a more sensitive circuit which has 16 comparators and a 4-bit DAC. Pretty much the same circuit. I've got a 3.1 volts 1 hertz signal. This has high resolution because it detects 0.5 volt changes in the input voltage rather than 1 volt, because it's got 16 op amps instead of 8. We have to have a bit more logic, but there's not an awful lot more, and it's still quite easy to figure out what that logic is. Now we've got a 4-bit sample and hold, just 4 flip-flops. They feed a 4-bit digital to analog converter. And this has high resolution because it has 16 discrete voltage levels rather than 8 with the 3-bit. And we use the same filter as before because our input voltage hasn't changed. We can see here analog input, digital output and analog out. There's many more steps in the digitized output, so that's going to give us a better overall representation of our input signal. It'll work better. Now we're going to make a real life input signal that's more complex than just a mere sine wave. So on Excel or Google Sheets, I'm going to put a time axis with 5 millisecond time increments, but you could use a lot smaller if you wanted to. This is just a demonstration going up to 1 second. And I've got a 1.8 degree angle increment every time the time changes. So all you do is divide 360 by the number of time data you have. Then Excel expects radians for trig functions, so we need to find the radians version of the degrees. And be careful, because you need to consider, will your complex wave be of suitable amplitude compared to your threshold voltages and the number of op amps you use, and will it be of a suitable frequency compared to your filter cutoff, even though you can change that. V1 is 1.8 times the sine of 6x, so its period is 6 times smaller than a normal sine wave. Then we'll have V2, then we'll add them together. So V2 is 1.3 times the sine of 30x. always use radians for the thing you're doing the sine of. And then V total will be the complex sum of the other two, just the two waves added together. And it'll be more similar to like voice or music than a simple sine wave. It's just a couple of sine waves added together. Then grab the time axis and our complex voltage, insert the chart just to see what it'll look like. So get rid of the text on the time column and the complex voltage column, because we need just data values for Multisim's arbitrary voltage source. Copy those, go to Multisim, go to sources, arbitrary voltage source, which just means we can put any XY data in, so time and voltage. Get rid of the old sine wave generator, wire this in instead. Double click on it once I've called it V complex. Get rid of the data that it gives you and paste your XY pairs in, time and voltage, and there they are. And don't forget to tick repeat, which will cycle your data over and over. I'll do a maximum time step of 3 microseconds and simulate. This is what happens if you don't click repeat data for the arbitrary voltage source. It stops at the last data point you entered. Isn't the end of the world, but it's not really what we want. Because I've got a higher frequency, because I've got a complex signal, I'm going to sample more quickly. And I'm also going to change the cutoff of the low pass filter. So I'm going to change it from around 160 microfarads down to 10 microfarads. You need to put a bit more thought into this in real life. Start our simulation. And there we are. We have our analog input voltage, the complex wave, and we have the digitized version, which looks pretty similar to it. But there's in and our analog out. So that's a fantastic result for such a simple circuit. So see if you can recreate results like this yourself. Because we've got a 16-bit ADC, it gives it a lot more resolution, and that looks amazing. So this is how we can create and visualize our own complex waveforms on Desmos. I've got V1 equals A sine BX with A and B sliders. And I've got V2 equals C sine DX with C and D sliders. And then I've got V total is V1 plus V2. And this allows us to look at what our complex waves are before we put them into the arbitrary voltage source and go through Excel. So as you change the sliders for V1 and V2, you can see them change. And when we add them together, we can get exactly what we want. And then we'd put this data in Excel. And this is what we did earlier. We had 1.8 times the sine of 6x added to 1.3 times the sine of 30x. So that is our waveform. And the more data rows you use in Excel, the better. Thanks so much for watching. I hope it was useful to you. Try and build your own. Use different complex waveforms and use the links in the description to have a play around with the files. Please like and subscribe, and all the best.